All right, looking at the second part of Chapter 7, back to Worksheet A. So starting off with problem number 2 for this one. So just some basic derivatives on this. We're kind of looking at kind of mainly the concept of the chain rule when we do a problem like number 2. So keep in mind for something like this, when you have an interior function, that means you have a function within a function. There's always one extra step you got to take, and that's how the chain rule works. So for this one right here, the basics of e to anything we know is that same item. So e to the negative 2x, the derivative of that is e to the negative 2x. But one thing we have to consider on this is an interior function. It's a function within this function. And so there's another part to this. And so part of that, the next step in the chain rule is to then multiply by the derivative of the interior function. So I have to multiply by the derivative of this, which is negative 2. And so that's just a super huge step on those that you can't forget, and they often are forgotten on a test, and people just don't do that. They end with that instead of taking this extra step. And so something you got to be careful on. Let's combine what we can. So negative 14 e to the negative 2x. And so that's where that one should finish. So moving on here to number 4. Again, you have just another use of the chain rule. So with this, basic power rule first, we would multiply the 4 to the front. So 1 minus 5x. Subtract 1 from the exponent. And that would put you here. But again, this is chain rule, so there's one extra step. If you stopped here, you'd get it wrong. You then have to multiply by the derivative of the interior function, which if you just focus in on 1 minus 5x as a function, if I said what's the derivative of that, right, the constant would go away, and we would just take the derivative of that term right there, which is negative 5. And so now you can throw that negative 5 in with the 4 and call that negative 20. But really important step in that chain rule process that you can't forget to do. So it's something you got to look for, got to recognize when it comes up, and make sure you take that extra step. A lot of points get missed because of that missing step in the chain rule process. So moving on to number 5. Just jump right down here. So again, with something like this, it's still just basic use of the chain rule, but one thing you want to consider is putting that into friendlier terms first. So instead of the cube root of x, I would write that as x to the 1/3 power. So that's basically our interior function right there. It's just easier with the derivative processes that we have. So again, we know that in the derivative process, e to x to the 1/3 is still e to x to the 1/3. But then this is an interior function that I can also differentiate. So we then multiply by the derivative of that interior function, which would just become 1/3 x. Subtract 1 from the exponent, and it becomes negative 2/3. And so that's what we have to multiply by. Combine what you can. I can do 1/3 of 6, which is 2. And then if you want to leave this as x to the negative 2/3, you can. Nothing wrong with that unless the directions specifically ask you to format it in a certain way, which they don't for this problem. So that would be an acceptable answer. If you wanted to take your x because it has a negative power and put it on bottom, you could certainly do that. And that would also be an acceptable answer. So I could move my x on bottom. I could also even put it back into radical form. So I can see there's a cube root. I can see there's a second power on that. And so if you wanted to take it all the way down to here, you can. Again, it's just a matter of following directions. If the directions don't say otherwise, then that would have been an acceptable answer right there. Number 6. Let me rotate here. So number 6, now we're looking at kind of the rule for differentiating a natural log, and this is something you have in your formula packet. So remember, you can always refer to that on a test, or if you kind of forget the rule, so you should always be familiar with those. But when we're differentiating a natural log, it just becomes 1 over that item. So in this case, I got to have 1 over 3x squared plus 2. And again, this is kind of the mistake a lot of people make on a test, is they stop right there. So remember, this is chain rule. This is an interior function. It's a function within the natural log. So we not only do the rule for natural logs, but because this is chain rule, I also have to multiply by the derivative of this interior function, which, if we use the power rule, would just be 6x to the first. So I have to multiply by that. And then just a little cleanup. Obviously, 1 times that is just that item. So 6x over 3x squared plus 2. And so this is the way we'd want to leave that answer. But don't forget this step right here. That's your key step that often doesn't get done in chain rule process. Moving on to number 9. All right, and again, to put this guy into friendlier terms before you go through the derivative process, so 2 minus 5x to the 1/2 power. So again, just basic chain rule on this. So we do the exterior function first. So we multiply the 1/2 to the front. And if we subtract 1 from 1/2, that brings us down to negative 1/2. But then again, we have this interior function here that we have to also consider. So we multiply by the derivative of the interior function, which in this case would just be negative 5. And so now we can bring a couple things together. Again, formatting is sort of up to you if the directions don't say otherwise, but one thing we should definitely do is simplify. So in this case, both of these terms can come together, so that is just considered simplifying, which you need to do. So negative 5 over 2 in front. If you want to just keep the rest of it as this, that would be acceptable. Obviously, you could take this whole term and put it on bottom. You can make it a square root instead of a 1/2 power. All those things are acceptable from here. And then moving over here to number 12. Again, put this into friendlier terms. So I'm going to bring my 1 minus 7x up to the top and give it a negative 1 exponent. This is just easier formatting for our derivative process. So now again, chain rule, I'm going to take my exterior function first, so multiply the negative 1 to the front. And if I subtract 1 from my exponent, it brings me down to negative 2. I then have to multiply by the derivative of the interior function, which would be negative 7. Just using the power rule. Combine what you can, so I should have a positive 14 in the front. And again, on this one, you can just leave it like this if you want. If you wanted to take this term and put it on bottom and make the exponent a positive 2, you could do that as well. Moving on to 15. So now given a curve like this where x is an element of the real number system, which it always is, so that's just sort of common notation, has a minimum at p, which is 4, 3, and a maximum at q, so find the values of a, b, and c. So we just got to figure out what those values are to put back into the original. Automatically, as soon as you see a word of minimum or maximum, that always means one thing. Those only occur where the derivative equals 0. So right off the bat, I can set a derivative equal to 0 to start working with that information. I'm going to refocus here real quick, see if that helps. Okay, so in this case, we can still do a derivative even though it has letters involved. We can still do that. So let me start by just putting it into a friendlier format. So that means I'm going to bring that x up top with a negative 1 power. So if I were to do my derivative process, so again, I'd be multiplying 1 to the front. If I subtract 1 from my exponent, that x to the 0 would go away. My constant goes away. Right here, if I multiply negative 1 to the front and subtract 1 from my exponent, so here's our derivative. And again, it's a minimum at this point. So I know I can set it equal to 0. And I can plug in a 4 for the x to get a little more information into that equation. And so there's one equation that we have. At a maximum, you have the same information. So at a maximum, also the derivative equals 0 at this point. So I can also plug in a negative 4 into this function right here to get a second equation. So both of those guys would be good equations to work with. But we really are only going to need one of those to move forward in this problem because both of those are really the same equation. This is going to give me 1/16. This is also going to give me 1/16. So really these are the same equation. If I were to get a by itself with either one of those, this is what we would come up with, is that a equals 1/16 c. If you wanted to kind of spin that around, multiply 16 over to here, you could also view that as 16a equals c. So either one of those would be helpful to us. So from here we can go back into the original function, plug in a few numbers. I know if I plug in a 4 for x, I can plug in a 3 for y. So let me move over here to some clean area on my page here. So I'm going to plug in the 3 for y. On this one, remember we said before that c equals 16a, so that's something else I'm going to be able to sub in. So for the a, I'm replacing the x with a 4. And again, that c is going to become 16a, so over 4. So with that, we can do a little cleanup on that. Let me get a little better equation to work with. So 3 equals 4a plus b plus 4a, which is obviously going to be 8a. So 3 equals 8a plus b. So there's one equation that we have. Let's do the same thing for this information to get a second equation. So now taking point Q, plugging in a -1 for y, and a -4 for x. So again, just doing a little cleanup on that one the same way I did on the one above it. So that's going to be -4a. This would also be -4a, which means it's going to be -8a. So -1 equals -8a plus b. So now if you just look at these two equations right here, if you remember, the process of elimination means I can just add those two equations together straight down and let these guys get eliminated. So if I just add straight down, I don't really need that plus sign there, but that's what I have. If I divide over, then I get 1 for b. And so now I have a value for b. I can sub that back in to get a value for a. So just pick an equation. So if I put a 1 right there and subtract that over, I get 2. Divide that by 8, and I get 1/4 for a. And then I can go back to any of my other equations that involve c. I can plug in the 1 for b, the 1/4 for a, and get a value for c that way. So go continue subbing back in, and you'll get your last value for c. But we're going to move on here. So moving on to number 16. We'll grab a new sheet. So given another equation, kind of like what we were just given up above, where p and q are real non-zero constants. So if c has a turning point at point p, remember a turning point could be either a max or a min or a point of inflection. In all cases, we know that at those points the derivative equals 0, so that's key. And it gives us some coordinates, so find the value of p and q. So we're actually doing pretty similar to what we did on the last problem. The only difference on this one is it's easier because you only have 2 unknowns instead of 3. So similar process here. I still want to start with a derivative. So 3x squared minus 2px. And then my constant would go away. So that's my derivative. I know this equals 0 at this point, so I can set the whole thing equal to 0 and sub in an 8 for x at the same time. So really important that you recognize that turning points or max or min or point of inflection, in all cases the derivative equals 0. So that's pretty much what those always lead you into doing. from here we can now solve for p. So 64 times 3, subtract that over, and then divide by negative 16 to get p by itself. So it looks like if we do that, it looks like p is going to equal 12 for us when we do that. I can now just go back up into the original function to solve for q. So if I take these points right here, I can sub in the negative 6 for y. I can sub in the 8 for x. And I can now sub in a 12 for p. And that is now solvable because it only has one letter in it. So do some cleanup on that and you should get your answer for q. Moving on to 17. So we got some stationary points on the graph. So find the coordinates of those stationary points. Remember, stationary points, turning points, all those guys, those are maxes and mins, or points of inflection. So again, they all tell you the same thing. Set your derivative equal to 0. So for this guy, if we first just put this into friendlier terms, I know I can set that equal to 0. Oops. I got to first take the derivative, then I'll set it equal to 0. So it's just taking the derivative right now. There we go. So setting the derivative equal to 0, and I can solve for x. So let me just start by subtracting the 2 over. And for this, I'm just going to put that x on bottom. So it looks like this. I would then multiply my x squared over to the left, which is going to give me this look right here. And obviously I could divide both sides by negative 2. So we come out with two potential solutions here, plus or minus 3. Don't forget the plus or minus, that's important. This one says find the coordinates, so they are looking for ordered pairs. So one is going to be with a positive 3, the other is with the negative 3. So in this case, remember the y values always come from the original function. So if you plug in a positive 3, you can get the y value for him. If you plug in a negative 3, you can get the y value for him. And that's where that one would end. Oh, there we go. So on 21, so we're given part of a parabola right here, just quadrant 1. And so we're given a rectangle below it. We're told that point B connects those two shapes. So for this, some key phrasing right here. It says the area of the triangle is maximized, which means if I can get an area function, according to this, it's a max, so I can set the derivative equal to 0. So for this guy, remember, how would you find an area of a rectangle? You would do base times height to get the area. So if you think about that, if I go x to the right and y up, I am at point B, and those dimensions would define the dimensions that we would use to get the area of the rectangle. So for point B, if I go over x and up y, and in this case we're told that this is a point on that graph, which means this y value, 3 minus 9x squared, can be his y value. So think of that as the coordinates for point B, which are the dimensions for point B of the dimensions of the rectangle. So we need an area function based on this. So we know area is going to give us that base times the height on this one. So let's distribute the x. All right, so that's our area function. And now according to this, because we're looking to maximize it, that means that's where the derivative would equal 0. So there's our derivative. If we solve for x, so subtract the 3, divide by negative 127, or sorry, divide by negative 27, and you get negative 1/9 for x squared, positive 1/9 for x squared. So 1/3 plus or minus is our value for x. In this case, we know it's a positive 1/3 because we are going to the right, and we're only in quadrant 1. So it would only be the positive x, but I want you to see something on this before we come to an end. That's all this one was asked for, but follow-up questions could be this. It could have said, find the max area. So in this case, now that we know that x is 1/3, I could have gone back to the area function that I have up here, and if I plug in the 1/3 into that function, I can then get the maximum area of the rectangle. So that's like a follow-up question that could definitely come with this type of problem.